So, quick question from the comment from the chat. On the answer key, it says see solution for an example. So unfortunately, the guided lecture notes are still a work in progress. Eventually, at some point, there was going to be a solutions guide available that would include like full worked out solutions. So that references something that in the future was going to be made, but is not currently made yet. So if you see in the answer key, see solutions, for example, it's unfortunately referencing something that does not yet exist. I am sorry about that. But thank you for bringing that up. So I did want to let everyone know that I have posted exam 1. It's a little longer than maybe a test I would give in the classroom. However, you have an entire 5 days to do it. You have today through Friday at midnight. It is due Friday, not Sunday. It is due Friday at midnight. So please make sure that you get it done before Friday at midnight. It's a little bit longer, but you have your notes that you can use. You can use a calculator. You have all that time to do it. Make sure you're showing all your work, every step. I want to see all the nitty gritty algebra. If you're thinking to yourself, am I showing too much? No. The answer is no. Make sure your work is organized. If I cannot understand the flow of your work, you will be marked down for that. I have to be able to understand what you're saying in order to give you credit for what you're saying. Please watch your notations. Watch the limit notation. Watch the limit notation. Where's my pen? Oh, this one's not linked up yet. Hold on. Let me pair this thing. Okay. Watch your limit notation. There's plenty of things for you to go look through to double check how that limit notation should look. We have the review that was posted. There's the notes. There's all the videos I've posted. There's online resources you can look at, but you need to watch your notation. You will be marked down for bad notation. I'm expecting you to kind of go over this the way you'd go over an English paper before submitting it. Give it a few once-overs. Make sure the algebra all looks good, all looks consistent. Make sure that your work makes sense. Make sure that it's neat. Make sure it's good before submitting it. I'm very interested in your work and not as interested in the answer. So a wrong answer with mostly correct work is going to get you most of the points, whereas a right answer with completely wrong work will get you no points. So make sure that your work supports your answer. Additionally, I do want to make note that using any math solving apps is strictly prohibited for the algebra, for anything. There's a lot of obvious things that those math solving apps do that make it pretty easy for me to point out when it's algebra that's not organic. Please don't make me go down the path of filing academic misconduct charges. I really don't like doing it. It makes me feel gross inside. So please just do not use math solving apps. Do not do the solutions that way. Please make sure all work is your own. You should not be collaborating with anybody else. No classmates, no tutors. It should be your work and your work alone. Once again, the sources that you can use are your notes and a calculator. So you shouldn't be researching the questions online, and in particular, you should definitely not be asking online message boards for help. Okay, so I think that's all I have to say about the exam. That is coming up. It is already posted. It is due Friday. The other thing to note, so for Chapter 2, there are exercises. So once again, the guided lecture notes are a work in progress. Section 2 does have exercises. However, as of right now, there are no answers to those exercises in the guided lecture notes. Those will be typed up and hopefully they're not going to be embedded in the lecture notes, but I'll post them as a separate document. hopefully the end of this week. You don't have any homework due this week. You just have the exam. Your next homework assignment is due next week, which I have posted what it is already, so you could start working on it early. But the answers won't be up until the end of this week. So just so you know, that's where we are on that. Yeah, I think that's all I have to say there. What I will say is we might be going a few minutes early today. I kind of have a wild week in front of me. Maybe I'll just pause this for now because this doesn't have to do with the class. Get back to business. So I know you're all here not to hear me chat about how tired I am, but actually about calculus. So I guess that's what we'll do today. But I am tired. Whew. Okay. So Unit 2.1, we're moving into Unit 2. This is where the real, I'd say, like calculus part starts. Limits are calculus, but like really when you talk about calculus as a math person, you're going to think of two main topics. You're going to think of derivatives and integrals. And in a typical, so if classes are split up into quarter systems, the way that the calculus sequence will work, you do Calc 1 is derivatives, and Calc 2 is integrals, and then Calc 3 ends up being multivariable calculus. But we are on a semester system, so this kind of, the way that calculus gets broken down is a little bit different because these three need to be split up over two. So what we'll end up having is we do all of derivatives, which again, big topic in calculus, and then you start integrals, and then in Calc 2, you finish integrals, and you move on to multivariable. But these two really, really big topics, derivatives and integrals, those are the really, really big topics of calculus. So we are moving in to one of the big things from calculus is kind of what I'm trying to get at there. All right. So from pre-calculus, you learned about the concept of the secant line. Well, maybe you did, maybe you didn't. Essentially, you talked about the average rate of change, and the secant line is a line connecting 2 points, and the slope of the secant line is the average rate of change. So if I come down to this picture here, the average rate of change from A to B is the slope of the line that connects these 2 points. So this y value is f of A. This y value is f of B. Remember that the formula for slope, y2 minus y1 over x2 minus x1. So the slope of the secant line, which we also know as the average rate of change between 2 points, how fast the y distance is changing between points, the average rate of change. If we're using this formula for slope, right, these are the x values, these are the y values. So y2, y1, x2, x1. So it's f of b minus f of a over b minus a. Hopefully looks or sounds kind of familiar. Right? That is the average rate of change. It's the change, the average rate at which the y values are changing between 2 points. Now, that was algebra. That was pre-calculus. But now we're going to get into calculus. And calculus says, hey, I don't care about the average rate of change. I don't really care about this line. I want to know what happens at a particular spot. I want to take these points and move them super close together, right? Look at this picture, moving them closer together. And this line between them is going to get closer and closer to being just this line that just barely touches this curve and tells you the change at a particular moment. The instantaneous rate of change is what we call it. Right, getting these points closer and closer together until finally you just have a line that just kind of sits, we call it tangent. See if I can draw a straight line here. Kind of, I like to say kisses the curve. It just kind of kisses it. And it tells you the instantaneous rate of change at that particular point. So this line here that just touches the curve in one place locally, that shows you what would happen if these points got closer and closer together, this line we call the tangent line. If you need to think about this in potentially a more like real sense, average rate of change, you could say that you are on a road trip and you start the road trip off at 0 miles per hour, and then after an hour later, going 60 miles per hour. So your average rate of change, if you're just using those two moments, right? If you're starting at 0 miles per hour and an hour later you're going 60 miles per hour, right? You're 60 miles per hour minus 0 miles per hour over 1 hour. Oops, that's not how I want to do that. Oops. Where am I going with this moment? Where am I going with this statement? I don't, my brain just, I didn't sleep much last night, guys. Basically, average rate of change is going to tell you the average rate at which you changed between beginning and end, the average speed you were going, right? So like on a road trip, you might start at 0 miles per hour, and then you might be going 20 miles per hour, and then you might be going 40, and then maybe you go back down to 20, and then you go up to 60. It's just going to average those numbers out, right? It's just going to average those. It's the average rate of change. Whereas instantaneous rate of change, this tangent line, that's going to be like your speedometer telling you at this moment you're going 20 miles per hour. Right? The tangent line is telling you right at this moment what's happening, how fast you're going. Whereas this average rate of change is telling you on average what you were going between two different times, if that makes any sense. Right? This idea of a tangent line is directly correlated with the idea of a derivative. So the derivative of a function we'll call the function f, which is denoted as, here's the notation. This is like an apostrophe right here. We call this f prime of x. So we say prime when we're talking about the derivative. The derivative is the slope of the tangent line. Right? So the derivative gives you the slope of the tangent line. Now, if we're thinking about this, about what's happening here, this average rate of change formula that we have going on up here is directly related to the slope of this line, right? Because the slope of this line, so let's see, we have these 2 points, they're getting closer and closer together. What if instead, maybe I'll just draw my own new graph over here. What if instead, drawing my brand new graph, say we started at an x value x, and then we went over a distance of h. The slope of that tangent line, which is going to give us this derivative, the slope of the tangent line, well, this y value would be f of x. This y value would be f of x plus h. Right? Same setup. I want you to know this is the same exact setup we have over here, but instead of calling this b, I'm just going to say, okay, we go over h. And we're going to call that x plus h. What we're letting happen is we're letting h get smaller until h becomes practically 0, i.e., h goes to 0. So the slope of that line initially, that's not the color I wanted, right? y2, so f of x plus h minus, let me label these for you. This is x2, x1, y2, y1, f of x plus h, so y2 minus y1 over x2 minus x1. But then we let, that's not a good limit sign. We let h go to 0. This is the slope, but we let h go to 0. And that will tell us what happens when these 2 points get so close together that they are essentially the same point. But this could simplify a little bit because you have x minus x in the denominator. So you just get an h in the denominator. And that right there, this right here, is the definition of the derivative. It's just slope. It's this picture. It's letting these 2 points get closer and closer together by using a limit. So f prime of x is equal to f of x plus h minus f of x all over h. There is another way of writing this instead of using the x plus h. So we use this one mostly. This is like the one we use. And if we were in the classroom, I would tell you you have to have this memorized. However, we're not in the classroom, and since you can use your notes on the test, I guess I can't tell you to memorize it. But if we were in a classroom, I would tell you to memorize it for the test. That's the one we use almost all the time. But there is a different definition that I guess is worth mentioning. The other definition, also a limit, is the limit as t approaches x of f of t minus f of x over t minus x. This gets used sometimes, not very frequently. There's some theorems that use this definition, but like I said, it's this one that we'll use for the most part. So these two formulas are describing the derivative of f at any value of x. That's important to remember. So this, I told you it's the slope of the tangent line, right? The derivative, very important if you're going to take away anything from today. The derivative will give you the slope of the tangent line at a point. It'll give it to you at any point on the graph. So this derivative, once you have it, you can choose any x value at all on this entire graph and find out the slope of the tangent line at that particular point. So you end up plugging in values to the derivative to find particular slopes. So the derivative itself will give you a function, but then you can plug in an x value and find the slope at a particular point. I'll be mentioning this frequently. This note number 3, we're going to say taking the derivative. And that process is called differentiation. So you can differentiate a function. You can take the derivative of a function. Some people try to start saying derive the function, but that's not the proper terminology. You don't say you derive the function. We can talk about taking the derivative of a function, but we'll talk about that more as we get further in. So there are many different ways that the derivative is written. So the one we'll use most is f prime of x, but some other notation that's worth mentioning. So we have f prime of x. Sometimes we also do dy dx. This one you'll see very frequently. Potentially df dx. And this notation, oops, that's not what I meant to write, also means taking the derivative of a function. So these all mean the same thing. In particular, these guys are the ones that you're going to see frequently. These are the same. They're identical. You might say, why would you have identical notation for the same thing? That just seems stupid. Why would math do that? Good question. Why does math do anything? So the short story is math was actually developed by multiple civilizations at similar periods in time without them talking to each other, and by multiple mathematicians without those mathematicians talking to each other. So multiple people came to the same conclusion of calculus at different times, and they all published their own papers, and that's how you get differing notation. I wish I could remember which notation belongs to which mathematician, and if my husband were here, he could tell you that, but I don't remember. All I know is that these are two different ways of writing the same thing, and that happens because people invented math at the same time in different places. All right, so I'm going to rewrite that definition of the derivative. So once again, f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. This is the definition of the derivative. Move that here. So a key fact, when you're using this formula to find the derivative, and we will learn faster ways later, it's just right now in this first section, we're using this method to find the derivative. There are faster ways. And if you've taken calculus before, because every once in a while I get a student who has taken calculus before. If you've taken calculus before, you'll note there's shortcuts. In this section, we're not using the shortcuts. And on the test, there will be problems that require you to use this formula. So the long way of doing this requires finding this limit. You have to find f of x plus h, plug it in, and then you simplify it until you get the derivative. Here's the key. When you're using this definition of the derivative, you are not done simplifying the limit until the h in the denominator has been canceled out. This h down here, this little guy right here, he will always cancel. Always, 100% of the time, cancel out. If it doesn't, you're doing something wrong. As you can see, what would happen with any function here, if you don't do any simplifying, if you just plug in 0, right, f of x plus 0 minus f of x over 0, you get f of x minus f of x over 0. You get 0 over 0, which is time to use a trick. Right, so that's why simplifying has to be done. All right, so I'm going to take this definition, I'm going to put this over here. We have a function, and we're going to use this definition to find the derivative f prime of x. F of x is equal to x squared minus 3x plus 2. So we have that portion of it. We have the f of x part, which is right here. We need the f of x plus h part, which requires you remembering how to plug in multiple variables to a function. So f of x plus h is plugging in x plus h instead of x in this function here. So you have x plus h quantity squared. Instead of x squared, it's x plus h quantity squared minus 3 times x plus h plus 2. Eventually, that's going to go right where this is. Let's simplify that algebra first. So this gets FOILed. You get x squared plus 2xh plus h squared. Distribute the negative 3 minus 3x minus 3h plus 2. So once again, x plus h squared is this part here. I just FOILed that out. Minus 3x plus h is these two right here. I distributed the negative 3, and then the plus 2 comes down. This is your f of x plus h. So right here, where you would have f of x plus h, I'm putting that in. Minus, so this is my f of x plus h, minus f of x is x squared minus 3x plus 2. And then this whole thing goes over h. So I'm just plugging in. This is just algebra. All of calculus is just algebra. I am plugging in x plus h to the function to get this first part. I then subtract the function I was given, f of x, and I'm putting it over h, and now I'm going to distribute the negatives and simplify. So I have x squared plus 2xh plus h squared minus 3x minus 3h plus 2. Distributing that negative, we have negative x squared plus 3x minus 2 all over h. Things are going to cancel, so these x squareds cancel. Negative 3x, positive 3x. 2, negative 2. We are now left with 2xh plus h squared minus 3h over h. Notice that everything on the numerator has an h in it. I can pull that h out. And the reason I do it this way is because oftentimes students will do something weird and they'll be like, these cancel, and then I'm done. But that doesn't quite work like that. You have to cancel the h out of every term that's in the numerator. So if you pull an h out, pull his h out, one h there, pull that h out, then you can cancel these h's. And once the h's have canceled, you can plug in. So you have 2x plus h minus 3. Now I'm plugging in 0, so I'm not going to write the limit. I have 2x plus 0 minus 3. 2x minus 3. I want to just kind of move that up just a tiny bit. So as our answer, we get f prime of x. Maybe I should use purple. F prime of x is equal to 2x minus 3. Now this doesn't look like a slope right here, but here's the thing. This guy right here, right, he's a parabola. Let's see, minus 2, minus 1. So he looks something like this. I don't know, something like this. If you wanted to find the tangent point at any particular location, you could just plug in that x value right there. And that would give you the slope of the tangent line at that point. So this function represents the slope of all tangent lines, and then you plug in a particular x value and you find the slope of the tangent line at that point, at a particular value. So once again, let's do another problem. So dg dt, that's the same thing as g prime of t. So we're finding the derivative of g. And we're using that same limit definition. So the first thing we're going to need to find is g of, this time we have t instead of x. So normally it would be x plus h, but we're going to do t plus h. So our limit that we're finding, the limit as h approaches 0, of g of t plus h minus g of t all over h. It's the same one as this guy, except for instead of x's, I have t's. And instead of f's, I have g's. And this will give me dg dt, which is the same thing as g prime of t. It's the derivative, it's just different names. So let's find g of t plus h first. So plugging in t plus h instead of t, so instead of this t, we have t plus h. So we have 1 over t plus h plus 3. And then g of t is just this original function, 1 over t plus 3. So we have 1 over t plus h plus 3 minus 1 over t plus 3, and then all over this h. It is just simplifying from here. So the common strategy for complex fractions is to multiply by the LCD on the top and the bottom. So the LCD here, even though they're very similar, it's going to be t plus h plus 3 times t plus 3. Remembering with your complex fractions, when you distribute, these guys will cancel on the first fraction and you're left with t plus 3. So you have the limit as h approaches 0 of t plus 3 minus, when these both distribute here, the t plus 3's cancel and you have this t plus h plus 3. In the denominator, you have h times t plus h plus 3 times t plus 3. Here's a cool tip. Never multiply out the denominator. Never multiply out the denom. Leave the denominator alone. The denominator is already factored. It is exactly the way it needs to be. Just leave it alone. So distributing that negative, we have minus t minus h minus 3 over h times t plus h plus 3. These t's cancel, these 3's cancel. And what I want you to notice, the similarities between this guy here and this guy here, notice that every term that had no h in it canceled, right? X squared's canceled, there's no h. 3x, those canceled, there's no h. 2, those canceled. Every term that doesn't have an h in it is going to cancel. So now you have negative h over h times t plus h plus 3. T plus 3, we're looking for that h in the denominator to cancel, and that's going to happen. So these h's will cancel. We have the limit as h approaches 0 of negative 1 over t plus h plus 3 times t plus 3. And now that the h's have canceled, you can plug in your h equals 0. So negative 1 over t plus 0 plus 3 times t plus 3. So you have negative 1 over t plus 3 times t plus 3, which you could simplify further to negative 1 over t plus 3 squared. You don't have to. These are both the same answer. But why not go that extra step? So dg dt is equal to negative 1 over t plus 3 quantity squared. So take a moment. I know this is a lot and we're very much switching gears from what we did before, but you are still using limits. We're just using them in a new way. And right now, it's like the page before it and this page are kind of at a disconnect because this page is dealing with the algebra of it, whereas the previous page dealt with the concept. And we will bring the two of them together where we bring the algebra and the concept back together. So if you're feeling a bit of a disconnect between what we're doing in this page and the previous page, that's okay. We will bring it back. Can I answer any questions? Take a moment to think, breathe, take a sip of coffee. And remember that this lecture will be posted so that you can go back to it. All right. So dy dt, this is the same thing as the derivative. Remember our definition of our derivative? I mean, I guess we could use the function name y. I don't really like using y of x. It just always looks weird to me, so I'm just going to pretend his name is f for a moment. So we're going to say f of t plus h minus, oh, not t. We're not doing t. Hold on a sec. Where did I see t's? This is dy dx. dy dx. F of x plus h minus f of x. Ooh, let me do those in color. I change my mind a lot, guys, and I really like color. F of x plus h minus f of x over h. Be really careful here. So for f of x plus h, there's a common mistake that would happen. And it's going to lead to problems. The common mistake would be to do this. And say that this is f of x plus h. Can somebody find an error for me in that? Aha, you didn't distribute the 3 to the h. Correct. So there should be parentheses here. And then the 3 gets distributed to the h. So just be really careful with your algebra. So you have the limit as h approaches 0. F of x plus h is going to be 3 times x plus h minus, oops, and I forgot, 3x plus h minus 4. I forgot to do this minus 4 here. Minus the square root of 3x minus 4, so that's f of x. All over h. Now here's the thing. This is no different. What's happening here? What did I do? Oh, there we go. Fixed it. This is no different than any of the other limits we've done, where if it's a 0 over 0 situation, which this will be, it'll always be that way with the definition of the derivative, we can just multiply on the top and bottom by the conjugate of the radical. So the conjugate, 3 times x plus h minus 4. Instead of a minus sign in the middle, we'll put a plus sign in the middle. But the insides of the radical will stay the same. Now, these two will multiply together and it gets rid of their square root. So you have 3 times x plus h minus 4. The middle terms will cancel because it's a difference of squares. These two multiply together and their square roots will cancel. So big parentheses, 3x minus 4. All over h times the square root of 3x plus h minus 4 plus the square root of 3x minus 4. Right, so I'm going to start distributing stuff. I'm going to distribute this 3, and then I'm also going to distribute this negative. So we have 3x plus 3h minus 4 minus 3x plus 4 over h times 3 times x plus h minus 4 I know some people don't feel this way, but I feel like algebra is really soothing. It's something that makes me feel really calm, and I know that's not how everyone feels, and I can understand why that's not the way that you feel if you don't feel that way. But try to maybe think about how algebra could be soothing. It's just very algorithmic. Go through the steps. Everything comes out nice in the end. Someone says math is fun when I know what I'm doing. It is. Just so everyone knows, I've cried many, many tears over math. My graduate program nearly killed me. I've cried so much doing math homework that you could probably fill a swimming pool with my tears and frustration. So if you think it's just that I'm great at math always, that's not the case. Math has moments of struggle for sure. But it's the getting past that struggle. So it's like with a Sudoku puzzle, you get stuck, and then you figure it out, and that like satisfaction you get from getting it right. Same satisfaction I get from doing math. And maybe you can put yourself in that mindset of like, thinking of it as a puzzle. It might help it feel a little bit more satisfying as you're working on it. Because if you're going to work on it anyways, you might as well make it feel satisfying. Anyway, so what's canceling? These 3x's cancel, and notice that they don't have h's in them. These 4's cancel, and they don't have h's in them. Now we have the limit as h approaches 0. I'm going to do the denominator first so that I can center the numerator for no particular reason other than I like to have my numerator centered. So what we're left with on top is a 3h. These h's cancel. Once again, I'm going to do the denominator first, just so I can center it. Now that the h's have canceled, that's the key step. We can plug in h equals 0. We won't write the limit anymore because we're plugging in h equals 0. I just wanted to center you. There you go. All right, simplifying. Now you could leave it like this. You have 3 over the square root of 3x minus 4 plus the square root of 3x minus 4. But these are actually like terms. So you can combine them together and you get 3 over 2 square root of 3x minus 4. You don't multiply them together. It's not like the square root cancels. It's just that you have 2 of them. And that would be your final answer. So dy dx is equal to 3 over 2 square root of 3x minus 4. So really, these are we're just doing limits again. There's like an extra step of limits. All right. So before I talk about this next key fact down here, I want to look at the next example. So the key fact makes a lot more sense when we talk about this example. So now we're going to be given a function, and we're going to be asked to find f prime of 1, and then to find the equation of the tangent line to the graph of f at x equals 1. So kind of a picture, 3x squared plus 1 will look a little bit like this, right? At x equals 1, you have this point right here, and this point has a tangent line, and we want to find the equation of that tangent line. So in order to find the equation of a line in general, you need to have a point on the line, so a point x comma y, and you need the slope of the line. For a tangent line, that's going to be plugging the x value in to the derivative. So let's talk about the forms of, I'm going to use the point slope form of a line. Which is y minus y1 equals m times x minus x1. Where x1 and y1, you could just put little ones there, are the point on the line, and then m is the slope. So the things that we need to find here, we need to find x1, y1, and m to plug into this equation. So what I was getting at down here, the m part comes from the derivative. So the key fact here, when we evaluate the derivative, f prime of x at a point, it tells us the slope of the tangent line at that point. So looking at this here, we want to find the equation of the tangent line to the graph at x equals 1. So this point right here is the point 1, comma, it needs a y value. So the x value we already know. The x value is 1. That's already done. The next step is either finding m or finding y1, but let's go with finding m. M, the slope of the tangent line, is the derivative evaluated at that point. In other words, m is f prime of 1, which is what it asks you to find right here. First, you're going to find f prime of x. So f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. So for the f of x plus h part, so my f of x is right here. Plugging in f of x plus h, we have 3 times x plus h squared plus 1 minus f of x, which is 3x squared plus 1, all over h. So foiling out x plus h squared, you get x squared plus 2xh plus h squared plus 1. Distributing that negative, we get minus 3x squared minus 1. All over h. I'm going to distribute this 3 out. So we have 3x squared plus 6xh plus 3h squared, and then plus 1. So the 3 doesn't go to this plus 1 out here because it's not in the parentheses. Minus 3x squared minus 1. All over h. These 3x squareds cancel. The plus 1 and the minus 1 cancel. What you're left with is 6xh plus 3h squared on top, and you can factor an h out. So you have the limit As h approaches 0, factoring out the h, you have 6x plus 3h over h. The h's cancel. The limit as h approaches 0 of 6x plus 3h, plug in 0 for h, 6x plus 3 times 0, it is just 6x. F prime of x is equal to 6x. Now, did we want f prime of x? No. We wanted f prime of 1. So here's all the work to finding f prime, but what we really want is f prime of 1, which you get from plugging 1 in for x. So 6 times 1 equals 6. So m is equal to the derivative evaluated at 1, which is 6. Now we need to find y1. To find y1, that's the y value here, you just plug into the original function, not the derivative. So y1 is f evaluated at x1, and x1 is 1. So it's f of 1, and that's using this function right here. So 3 times 1 squared plus 1. Maybe I'll make a note here just so you can see. F of x equals 3x squared plus 1. So that's 3 plus 1, which is 4. So y1 equals 4. You now have everything you need to use this. To use our point slope form of a line. So it's y minus y1 equals m times x minus x1. y1 is 4, so y minus 4. M is 6. And then x1 is 1. We can now distribute and solve for y. So we have 6x minus 6. Adding 4 to both sides, you get y equals 6x minus 2. Right? So if you're trying to find the equation of a tangent line, which this happens frequently, you're first finding that slope, which requires finding the derivative, and then plugging in the x value. Then you have to find the y value, which comes from plugging in your x value to the original function. And then you put it all together. So maybe what I'll do is kind of summarize right down here. Let's use pink to summarize. As a summary, To get slope, which is your m value, you plug x value into derivative, which is f prime of x. To get the y value, which is y1, you plug the x value into the original f of x. And then you can put it all together because you need x1, y1, and m. All together gives you the equation of the line. Any questions so far? Right. I'm going to stop and mute myself for just 1 second because a committee I'm on is sending me messages that are actually, I have to look at those right this second. So just give me 1 moment. If you have questions, type them out. All right. Only moderate fires to put out. Deep breath in, deep breath out. Alrighty. It's a big enough problem that has to be dealt with later. When it rains, it pours. All right, so let's move on to another example. So for this problem, we're being told that the derivative of a function is 3x squared minus 2. They're just telling us. No work needed, they're just telling us. It says to determine the equation of the line tangent to the curve at the point 2, 9. So remember, y minus y1 is equal to m times x minus x1. That's the equation of a line in point slope form. Oh yeah, everything it's fine. It's fine enough at least. Anyway, so that's it in point slope form. We need to find x1, y1, and m. But here's the thing. They gave us a point. This point 2, 9, that 2 is your x1, that 9 is your y1. That's already done. The only thing left to find the equation of the tangent line at this point is to find m. And m is what you get when you plug x into the derivative, and x is 2. So f prime of 2 is the slope of the tangent line at x equals 2. And here's that derivative we have right here. They told us that y prime is 3x squared minus 2. Right? So plugging in 2 into that derivative, we have 3 times 1 squared minus 2. So 3 minus 2 is 1. we now have everything we need to use our point slope formula. So y minus y1 equals m times x minus x1. Our y1 is 9, our m is 1, our x1 is 2. So y minus 9 equals x minus 2. Just add that 9 to the other side and you get x plus 7. Y equals x plus 7. I feel like I did something wrong here. I did. Don't mind me, my brain's just in a million other places. This is supposed to be a 2. Here's what I did wrong. That's supposed to be a 2. 2 squared is 4. 4 times 3 is 12. Minus 2 is 10. This is 10. This is 10. This is 10. And this is not right. So this is 10x minus 20. 10x, add 9 to both sides, minus 11. So there's a lot of really fun questions that you can do with these derivatives. For this next example, we're told a function and its derivative. So let me just kind of like write this. The original function that we're given is 1/3 x cubed minus x squared minus 7x plus 2. The derivative, which they've already given us, we don't have to find it ourselves, is x squared minus 2x minus 7. And we want to find this shouldn't say points, this should say x values. Well, we're just going to find the x values where f of x has a tangent line with a slope of 8. So let's decipher this. F of x has a tangent line with a slope of 8. The tangent line has a slope of 8. So that means that f prime of x, that's the slope of the tangent line, is equal to 8. We want the x values where f prime of x is equal to 8. So here's f prime of x. We want this to be equal to 8. So we have x squared minus 2x minus 7, that's the derivative, has to be equal to 8. We want the derivative to be equal to 8. This is just a quadratic. This is no big deal to solve. We can subtract 8 on both sides. X squared minus 2x minus 15 equal to 0, and then we just factor. This is x minus 5 times x plus 3 equal to 0. X equal to 5, x equal to negative 3. Those are the two x values. Those are the x values where the slope of its tangent line will be 8. Because if you plug in these values, you should get 8 out. All right. So this next thing is really something we're not going to use a lot right this second. We're going to use it later. I don't even know if I want to talk about this key fact number 3 right now. We're not going to use it right this second, so I think I'm going to come back to it when we actually use it. So I'm just going to ignore it and we will come back later. It even says more on this later. All right. So differentiability. So differentiability has to do with the derivative. Essentially, differentiability means that you can find the derivative at a point. So we say that f is differentiable at x equals a, as long as the derivative there exists. So as long as f prime of a exists. If the derivative exists everywhere, then we say it's differentiable everywhere. But this is kind of a weird thing to think about algebraically and makes a lot more sense if you think about it pictorially, graphically, if you will. So this can happen with discontinuities. So let's imagine a graph. I have a hole in this graph, just a removable discontinuity. I can't find a tangent line here because there's no point there to find a tangent line, right? There's nothing there. It's an open hole. So if f of a doesn't exist, it's impossible for f prime of a to exist. F of a has to exist in order for it to be differentiable there, for the derivative to exist there. But just discontinuities in general, even if you had a point, even if this was filled in, it would, like, if not filled in, if you had a different point up here, even if you had this going on, you'd still have a problem. That still wouldn't be differentiable there. Because there's a hole in the graph. It's discontinuous. If you're discontinuous, you cannot be differentiable. Sorry, hold on just a second. All right. So other kinds of discontinuities we have these jump discontinuities. So we can't be differentiable here because it's like they're not even connected. Like, how would you draw a tangent line in here? I don't even know how you would draw it, right? Because they're just disconnected. So if you're discontinuous, you can't be differentiable there. Another thing you could have like an asymptote, like a vertical asymptote. So like, boof, like this. In either of these cases, you're discontinuous at A, so f prime of A won't exist. So you can't be differentiable if you're discontinuous. That's one thing. The other thing that can be a problem is if you have a corner or a cusp, which begs the question, what is a corner? What is a cusp? Right? In this picture, this guy right here and this guy right here, these are corners. They're not differentiable there because at this peak right here, how would you draw the tangent line? Would you draw it like this? Would you draw it like this? Would you draw it? You could draw it anyway, right? So it's not like the tangent line for a straight piece is it's just that piece itself. So you can draw tangent lines on this. You can draw tangent lines here and here, but on these corners, there's no telling what you can do. So if you have a corner or a cusp, I'll draw a cusp next. If you have a corner, you're not differentiable there. So a cusp, similar idea. You have this pointy part, and you can't be differentiable at a pointy part. If it's a pointy part, it's not going to be differentiable. So you can't be differentiable at a cusp or a corner. And then the other weird thing you can run into this is a really weird one. But like if you tried to take a tangent line right in here, this would be a vertical tangent line. And a line that has a vertical slope is actually undefined. Like a straight up and down this line has an undefined slope. So in this picture, at x equals 0, the tangent line is vertical. Which means undefined slope. Which, if the slope is undefined, that means, oops, that means f prime of 0 is undefined and therefore doesn't exist. So here's the big story. If you're differentiable, you have to be continuous. It's not enough to be continuous does not mean differentiable. Always. So differentiable always means continuous. However, on the other hand, continuous does not always mean differentiable. So it's not a two-way street. Differentiable always means continuous. Continuous does not always mean differentiable. But most importantly, this means if f is not continuous at x equals a, not continuous at x equals a, i.e. discontinuous continuous, why does that word look weird? I.e. discontinuous at x equals a, then f can't be differentiable at x equals a. Right. So if f is not continuous at x equals a, let me just kind of move stuff around so it makes more sense here. So if f is not continuous, i.e. it's discontinuous at x equals a, then f is not differentiable at x equals a. Therefore, f prime of a does not exist. I'll give you a moment to write that down. So I'm not going to actually talk about left and right hand limits here for discontinuity. I'm just going to ignore this one, right? And I'm also going to not do example 2.1.8 since I'd want to talk about this one. I think this is the last one in this section. Yeah, it is. I want to talk about this graphing problem, and we have about 8 minutes left, so I want to talk about this one with the time we have left. So let's talk about this graph. Right. So looking at this graph, we're looking at which values of x is f discontinuous. So remember, that's where you have to pick your pencil up. So tracing. Oh, there's an asymptote here. So we're discontinuous at, that would be x equals -4. And then we start tracing again. Okay, that's fine. We're still continuous. Oop, hole in the graph. Discontinuous at 2. All right, oh, there it jumps right here. So we're discontinuous at 5. And then it goes off there. So we are discontinuous at -4, 2, and 5. I don't know why. Oh, maybe what I'll do here. I was like, why is there so much room? But you know what? We can do a little better here. So at -4, it's discontinuous because that limit doesn't exist, right? Goes this way. Left and right hand limits aren't equal. So this is because the limit as x approaches -4 of f of x does not exist. The second discontinuity was at 2. And notice here, the limit exists, right? They approach the same y value, but the actual value is different there. So the limit is not equal to f of 2, even though both of them exist. And then at 5, we have the problem of the limit not existing, right? They approach different y values from the left and right. So that's discontinuity. Then we talk about differentiability. At where is it not differentiable? So first of all, I can tell you that if it's discontinuous, we know it's not differentiable there, right? So we can start by listing those ones. We are not differentiable at x equals -4. I'll just list it like this: -4, 2, and 5. Because not continuous, because discontinuous there. Discontinuous. There. Right, so then we're going to look for other places where we're not differentiable. So this is all good. We're differentiable here. Discontinuity, we already caught that. Oop. Here's a cusp. So that's at x equals -1. We're not differentiable. And that's because there's a cusp there. Okay, so we weren't differentiable here because of a discontinuity. Here, we're not differentiable because of a discontinuity, but we already got that one. Here, we're not differentiable because of a discontinuity. And then here is a corner. So that's at 9. We're not differentiable at corners. So basically, you're looking for discontinuities, right? Which we know how to find those, and then cusps and corners. And then, yeah, that's basically all you're looking for where is it not differentiable. So it says to find the values of f prime of -7 and f prime of 8. Let me just write those over here. Find f prime of -7 and f prime of 8. So this is -6, this is -7. So this point right here, remember, f prime of -7 means the slope of the tangent line at -7. So if I drew a tangent line in here, that tangent line would be a horizontal line. And the slope of a horizontal line is 0. Now let's look at f prime of 8. So let's see, 6, 7, 8. We're looking at this point right here. So his tangent line, a little bit different. His tangent line just lays right on top of this line here. His tangent line has the slope of whatever this line right here has. And to find the slope of a line, y2 minus y1 over x2 minus x1, we just need to find the slope of this line. And you can use 2 different points on the line. So you can use this point right here, which is the point 9, 4. And I know this doesn't look like a point because it's an open circle, but we can still use it for finding slope. This is the point 5, -4. So x1, y1, x2, y2. Plugging in here, 4 minus -4 over 9 minus 5. So 8 over 4. F prime of 8 is equal to 2. So once again, I know that you're probably not going to look at this homework for a while because if you haven't finished your homework 3, you're probably still working on that. That's due tonight, and then your exam is due on Friday. So I understand you probably won't look at this homework for a while. If you do try to start it, the answers will be, like I said, posted on Friday. Hopefully by Friday, the answers for the homework will be posted. Otherwise, you'll just kind of have to do problems without those answers there. But I think you'll probably be working on the exam, so it won't be a big deal. If you have questions, let me know. In terms of the exam, I won't answer any questions on how to do any problems. I won't answer questions on whether answers are right or wrong. But I will clarify any wording if you are confused about wording on the problems. So feel free to send me messages about that. All right, so I am going to let you go 10 minutes early so that I can maybe eat food, drink water, and do some jumping jacks before I do another 3 hours of meetings. All right, everybody, have a fantastic day.